Hello students, welcome to my channel Arun's Physics Portal. In this lecture, I will discuss about the Butterworth first order low pass filter. This topic is useful for MSc Physics and Electronics students and also for BE and BTech students of EEE and EC branches. The JRF and NET aspirants will find this topic useful. The complete note of the topic is given here for your convenience. I hope you enjoy going through it. Now let us come to the topic. Before describing the Butterworth's first order low pass filter, it is better to have a look at the passive low pass filter. A passive low pass filter is shown in the figure 1. We have a resistor and a capacitor connected in series, and a potential Vi is applied across this combination. The output is taken across the capacitor C. Since R and C are connected in series, the same current flows through both of them, and therefore the current I in the circuit is given by I equal to Vi upon R plus 1 upon Sc, where S is equal to j omega, or I equal to Sc upon 1 plus Src into Vi. Output across the capacitor is then current into impedance of the capacitor. So this is V naught equal to I into 1 upon Sc. So this is Sc upon 1 plus Src into Vi into 1 upon Sc. So this is equal to 1 upon 1 plus Src Vi. The gain is the ratio of output by input. So the gain is V naught upon Vi is 1 upon 1 plus SRC, and this is equal to 1 upon 1 plus j omega upon omega h. And the magnitude of the gain is AV equal to 1 upon root over 1 plus omega upon omega h whole square. ये कैसे आता है? We know that if a quantity is complex, we can express it as x equal to a plus jb. Its magnitude is mod of x equal to root over a square plus b square. तो ये भी आपकी कॉम्प्लेक्स क्वांटिटी है, तो इसका जो मॉड होगा वो इतना होगा. दिस इज द वैल्यू ऑफ दिस. ओमेगा एच इज 1 अपॉन आर सी एंड दिस इज द अपर कट ऑफ फ्रिक्वेंसी. इक्वेशन 1 को ऐसे लिखने के बजाय हम ये भी लिख सकते हैं ए वी इक्वल टू since omega is 2 pi f. Okay, so we can write AV also as 1 upon root over 1 plus f upon fh whole square. ठीक है, इसको ऐसे लिखिए, you write it like this or you write it like this. So from this equation 1, following conclusions may be drawn. So this is the frequency response curve of this. On the x-axis we have frequency omega, on the y-axis we have gain. Since we have seen the maximum gain is 1, so we have written here 1. So from equation 1, if omega equal to 0, then AV is equal to 1. Okay, the gain is maximum when omega is 0. As omega increases, AV decreases. This is so because omega appears in the denominator of equation 1. So as omega increases, AV decreases. When omega equals omega h, a particular frequency, then what we get? We have then AV equal to 1 upon 1 plus omega upon omega h whole square. This is our equation 1. Okay, so omega and omega h are equal. So this ratio is equal to 1. So this is 1 plus 1 is 2. So this is 1 upon root 2. And as omega tends to infinity, AV tends to 0. So this is the frequency response curve of the passive low pass filter shown in figure 2. So the frequency at which the gain falls to 1 by 2 times its value at omega equal to 0 is known as the higher cutoff frequency or upper cutoff frequency. Okay, now we come to Butterworth's active first order low pass filter. See here, this figure enclosed within the red line is your non-inverting amplifier whose gain is 1 plus Rf upon R dash, and this I write as G. Here we have a resistor and a capacitor in series, और इस जंक्शन से इनपुट दिया गया है नॉन इन्वर्टिंग टर्मिनल को ऑप एम्प के. द अप्लाइड सिग्नल इज Vi is applied here at one end of R. The potential at this point, which is connected to the non-inverting input of the op amp, is Vi dash. So we have the gain of the inverting amplifier is 1 plus Rf upon R dash. This I write as G. So this is here. Since no current flows into the non-inverting input of the op amp because of its extremely high input impedance, all the current that flows through R will flow through the capacitor C. Okay, so the current I is Vi upon R plus 1 upon Sc, where S is equal to J omega, or I equal to Sc upon 1 plus Src into Vi. So the potential Vi dash at the non-inverting input of the op amp, ये कितना होगा? This is the potential across the capacitor, isn't it? Because one end of the capacitor is grounded. You see from the figure, this is your Vi dash. This goes to the non-inverting input of the op amp. Okay, and here we have capacitor. This end is grounded, so potential is I into 1 upon Sc. Clear? Put the value of I here. So I is equal to Sc upon 1 plus Src, Vi into 1 upon Sc. So Vi dash is 1 upon Src into Vi. Okay. So note that the input to the op amp is not Vi, it is Vi dash. Whatever the potential is applied to the input of the op amp will be amplified. The signal is not at the input of the op amp. Signal at the input of the op amp is Vi dash. So we have to find the value of Vi dash. That's why we have calculated here Vi dash. Okay. So the output V0 is therefore V0 is 1 plus Ra by R dash into Vi dash. Put the value of Vi dash here. So we get as V0 is 1 plus Rf upon R dash into 1 by 1 plus Src into Vi. So the gain is V0 upon Vi. This is the gain of the op amp. So this is 1 plus Ra by R dash into 1 upon 1 plus Src. This follows directly from this expression. Bring Vi here. So this is V0 upon Vi. This is equal to 1 plus Ra by R dash into 1 upon 1 plus Src. So this is 1 plus Ra by R dash into 1 upon 1 plus J omega upon omega h, where omega h again is equal to 1 upon Rc. And this is your higher cutoff frequency or upper cutoff frequency. Okay. So the magnitude of the gain is AV is mod of Vi upon V0 upon Vi. This is 1 plus R by R dash into 1 upon under root 1 plus omega I omega h whole square, where omega h is the upper cutoff frequency. Okay. So from equation 2, what follows? At omega equal to 0, AV equal to G. This is maximum gain. As omega increases, AV decreases. Why it decreases? Because omega appears here in the denominator of right hand side. So if omega increases, AV definitely decreases. As omega equal to omega h, When omega equal to omega h, then this term becomes equal to 1. So this is 1 plus 1 square is 2. So this is 1 upon root 2. And then this is g. So this is g upon root over 2. As omega tends to infinity, AV tends to 0. ठीक है, यहाँ देखिए ओमेगा इन्फिनिटी को जाएगा तो दिस डिनोमिनेटर becomes infinite. So AV tends to 0. So the frequency response of the active low pass filter is shown in the figure 4. So on the x-axis we have frequency, on the y-axis we have gain. So the gain falls as the frequency increases, and at omega equal to omega h, the gain falls to g upon root 2, or this is 1 by root 2 times its gain at omega equal to 0. The slope of this curve is minus 20 decibel per decade. This means that when the frequency increases by 10 times, the gain falls by 20 decibel. Okay. So the Butterworth active low pass filter has a constant gain A, AV from 0 Hz to FH. Beyond the higher frequency cutoff FH, or you can write here omega h also, because omega h is 2 pi FH. Beyond the higher frequency cutoff frequency FH, the gain falls at the rate of 20 decibel per decade. It means that the gain falls by 20 decibel each time the frequency increases by 10 times. The other equivalent terms for the cutoff frequency are minus 3 decibel frequency, break frequency, or corner frequency. So this is all about the Butterworth first order low pass filter. This is very simple. I assume that you like this presentation. यदि आपको मेरा यह प्रेजेंटेशन अच्छा लगा हो तो इसे लाइक करें, शेयर करें और मेरे चैनल को सब्सक्राइब करें. So thank you for watching. See you next time with some other topic of interest. Till then, goodbye.